what's going on YouTube? I think that we should be live now. Today is June 12th, 2026, and we have a special stream today. For those who don't know, well, first off, if it's your first time here, welcome. My name is John. I am practicing mathematics live. I am working in a spiral structure. I always like to draw this. And part of this is that I started out doing linear algebra. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, perfect. I did linear algebra for one stream, chapter 1. Then eventually I got to chapter 10. After that, we started doing calculus, linear algebra, and then we added representation theory for one stream. After that, we did calculus 1 through 2, linear algebra 1 through 10, like 10 streams of linear algebra, 2 streams of calculus, and then 2 streams of representation theory. Today, well, yesterday, I suppose, we just completed this last cycle. Calculus, 3 streams of calculus, 10 streams of linear algebra, and then 3 streams of representation theory. So you see how I'm resetting and I'm reviewing. I'm like coming back and reviewing math again and again, coming back to the same topics, which I think is annoying some people, but I think it's a smart way to work. So in this direction, we're getting depth. What's up, Mizzy? Good to see you. In this direction, we're getting depth. In this direction, we're getting breadth. Right? And so if I kept drawing this thing, it would be like we have 3 streams of calculus, 10 streams of linear algebra, and then 3 streams of representation theory. Now, what I'm trying to get at is that during the reset, I don't know if this is a different color or what, but during the reset, and when we start like a new cycle, we've got some kind of special stream. And today is a special stream. It's a special reset stream. It gives me a chance to do something off topic, so that I'm primarily staying focused on a few subjects, but I do want to hit other subjects. I do want to hit other types of math. And today we're going to be talking about WTF is a universal property. Someday I'll do a stream on the Lambert W function, bro. Manu loves coffee. I love coffee too, bro. So today we've got some category theory in context. Dude, I'm really looking forward to this. Lockheed something or other Starfighter. His handle is different in the Discord versus the stream. But Starfighter over here, he back on freaking May 23rd. Today is actually June 12th. So it's been a while since he gave this amazing exercise in my Discord. By the way, everybody, shout outs to the Discord. You can get to it, link in the description, or link in bio, all that good stuff. Or this short link will take you directly there. This will be an updated invite link. So Discord is a nice little chill community, and he gave this really nice comment about it related to the tensor product stuff. The topic came up at some point about the tensor product of vector spaces or something. I hope the concept of direct product of vector spaces is a bit less overkill. This time I did check your textbook. He was working from the 3rd edition. Unfortunately, this amazing book is out of print, so the best you can do is find it online. Anyways, we I read all of this, and I got this in a stream just a few days ago. This is talking about some really cool currying of functions. I'll pause and let you read this. I wish I could. I really should have gotten like a more shrunk, like a smaller width version of this message, but if anybody wants to pause and read this, I'll give you an opportunity to do that right now. So if anybody wants to read this, this is your chance. Go ahead and pause the video and try to read this first part. So we did all this stuff on stream the other day, and this was reading some stuff in chapter 3 of this amazing book. The topic was called like a universal property or universality of vector spaces or something like that. Section 3, linear transformations, the optional final subsection of one of these, not inner product spaces, but where is it? We have an optional section in here somewhere. Where did it go? Where did it go? Okay, it's earlier. It's not representations of linear transformations. It's maybe in section 2. Basic concepts of vector spaces, maybe? Or earlier. No, earlier. 186. Yeah, in section 3.1. We've got section 3.1 on basic concepts of vector spaces. This sparked an interesting discussion. There's this topic about the universality of function spaces. Let me remind myself what this meant. So what I remember is that we have some definition where I believe that we were extending, noticing that the definition of f plus g, which takes, we begin with r cross r and returns a new real number. Well, f plus g defined on a point x, actually this only depends on the addition structure in the codomain. This addition is only defined in the target space, in the codomain R. So we, at no point do we need to use a composition in the domain, and that's, I believe, true. Yeah, for f plus g, and I believe also we have the same thing for the function rf of x is r times f of x. This only depends on the multiplication in the domain. So that hints that we can actually extend this, because we never actually defined, we never actually required that the input to the functions is a real number. This implies, oh wait, f plus g, oops, this isn't r cross r, this is just r to r. Oops, my bad. But we can replace that domain with any function on a set, on an arbitrary set, which is neat. And then I believe that you do things like defining a function from a set to the real numbers, and we call this like vector space 1 or something, because each of these function spaces is itself a vector space. And then vector space 2, because we can define again a function space from any yeah, we can extend this even further by noting, like, what is it that we really need? We need addition and multiplication, and then I think that we'll ultimately need some of the other vector space axioms, but we can extend this and define function spaces for any set into a vector space, into any vector space. So we need addition and we need multiplication, and I believe that we'll also need the distribution axioms of a vector space. So then in V2, we can again define a function, the vector space of all functions mapping an arbitrary set into V1. So, and then V3 is now the set of all functions that map from a set into V2. And if you keep doing this, you keep, quote unquote, mathematicians who study this are, we better stop here, or so, like, what is the exact line? It's really funny. But yeah, the author says, oh, we better stop here. Otherwise, mathematicians who keep studying this stuff and keep doing this are climbing the ladder, quote unquote. And I believe that this is kind of referring to some sort of ordinal numbers and like counting of different sizes of infinity or something like that. Let me read exactly this line, because I'm not a mathematician, dude. I'm just trying to understand this stuff. So, thus, starting with the set S, we could consider the vector space V1 of all functions mapping S into R, and then the vector space V2 of all functions mapping S into V1, and then the vector space V3 of all functions mapping S into V2, and then, oops, we better had stopped now. People who do too much of this stuff are apt to start climbing the walls. Parentheses. However, mathematicians do sometimes build cumulative structures in this fashion. So I learned the other day on stream that this is called currying, and this reminded me, this is exactly matches my intuition, because these are defined as functions mapping from one object into functions mapping the second object mapping into ... So this is super cool. This reminds me of functional programming, where you can curry any function. This is exactly currying from functional programming, and it's amazing to me to see currying actually in pure mathematics now. So we're all used to, if you're writing Python or Ruby or something, defining a function with two arguments and then returning a third number or object or something. But you can also define this as a function of one argument, which then returns a function g, which takes b to c. I hope that this somewhat makes sense. So the function a returns a function g, which the function g returns b to c. So then you can apply function a, and this is a partial application to the function, and now this is a function g, which then you can evaluate at your second argument and get your final, right-hand side, the solution. What's up, Lockheed Blackbird 127? How's it going? A relative search term is cumulative hierarchy. Exactly, dude. This is super cool. What's good, dude? Whoa, me mentioned. Yeah, dude. You're on the thumbnail today, bro. You're on the thumbnail. So I'm just gonna call you @Lock because your name is different everywhere, and I heard that that's what the cool kids are calling you. But in the it confuses me, dude. Your name confuses me because I'm like, oh, he's Starfighter. I know you as Starfighter in my Discord, but then on the stream, I guess people know you as Lock. So I'm just gonna call you Lock in the title. What's up, dude? Congrats on the big hundo. Thanks, man. Thanks, Arad. Yeah. 100 days, and I solved my first real representation theory problem on day 100, which was freaking awesome, I think. We got there yesterday. I finally solved my first real, true, new math for me problem on day 100. It's kind of nice, I mean, I learned a lot of freaking, new linear algebra before, but still, there's something like quite special to me because one of my goals is learning new math live and trying to showcase how I learn math, as a quote unquote hobbyist or somebody returning back to math. So he has the same PFP as Lockheed. Yeah, turns out it is the same person. It is the same person, which is confusing to me. So, the von Neumann universe, hell yeah, dude. Okay, so this is called, you're saying, I should give you like a nice little, color for the rest of the stream today. You've got Clippy, which is cool. I know the reference. I like it. You've got Clippy with like a piece of paper behind it or something. But I need to look up, so a search term for this is cumulative structures. Cumulative structures. And it reminds me of, power sets of sets and getting, to new ordinal numbers or cardinal numbers, like, defining bigger sizes of infinity, cardinal numbers or whatever. I don't know. I don't know this stuff. I want to learn it. Von Neumann universes. Dude, that sounds cool. What the hell is that? That sounds like something I want to look up. I think I understand what you mean by cumulative structures, but I do want to look this up. To do von Neumann universes. Hell yeah. Fun fact, Turing is an adjunction. Hell yeah, dude. Hell yeah. Okay. So today, I am going to try to understand this beautiful freaking exercise that you gave me on Discord, which is, such a freaking gift, man. Thank you for this like deep exercise. Like, you wrote up so much. I feel bad, taking this long to respond and try to work this exercise. Like, you wrote it up with, like, hint tags and everything. And this was, a while ago. This was on almost a month ago. So, today is a special reset stream. I'm going to try to understand what the hell a universal property is. As you can tell, you can tell that's the goal for today's stream just from the title, right? Okay. It is an example of cumulative hierarchies. Right. The von Neumann universe is literally iterated power sets. Okay, cool. So I knew about this. I knew about iterated power sets. Like that you can. I don't know how this works. Like, you say x is r or something like this, and then what do you do? Like 2 to the x or something like that. I don't know, dude. I don't know. I've heard of this kind of stuff, like, but I haven't. I don't feel like I've ever really understood it properly. Do you know how to get a feel for how AI, computer science, physics, maths, or another technical subject is done in university prior to picking a course? I'm not sure. I mean, I think I could talk about related things to that cyber potato. But first, let me take a quick break because somebody just mentioned coffee, or their name was Coffee or something. I need some coffee to be able to power through this. I just realized I left it in the other room. Okay, so be right back really quick. There's a little introduction, a goal for what today's stream is going to be. If anybody wants to work this exercise yourself, this amazing exercise from Locke, you can join the Discord. There's a link in the description, or there's an easy to type URL. Yeah. All right, BRB. I'm going to get my coffee real quick. By the way, did I mention that I am also a classical guitarist? I have a second channel, and you can find a link to that in my home tab. So be right back. Okay, I'm back. So, all the background music is me. Oh, look at that. We got the chaconne. This piece is actually objectively like one of the hardest classical guitar pieces, and I frickin' did it as a hobbyist. Hell yeah. Let's go. Discord, just let me know if the music should go up or down and things like that. So I'm going to try to work this problem today. As I said, we already covered this first chapter, or this first paragraph from this exercise last time. And now we're going to get to the main meat. That sounds good. The above discussion constructed the direct product from the inside. Let's see, why... Oh, is this the direct product? Okay, wait. The textbook didn't use the word direct product, but I guess... Oh, I think I need to understand a little more of what you said here compared to the book. But, okay, it almost... I see, you said that this section almost covers it. It kind of hints toward... direct products, right? The last optional subsection on page 186 shows how the set of functions... Oops, I need to make sure that the iPad is always keeping up to date. Yo, what's up, y'all? Arad, how's it going? Perfect timing, I'm back too. Hell yeah, dude. Leo's allergic to that Discord link. Probably because it is, Discord is, probably not good for your attention span. But I promise I try my best to keep my Discord chilly, and just like, my goal is that this Discord is not like an attention-sucking thing. I don't know if it's set up correctly, but I try to disable all notifications by default, which I find important because a lot of people don't know how, you know, to turn off notifications, and some Discords are just so damn noisy, dude. So I find it important for me to try to, you know, keep it chilly, as I say, as I always say. So if you want notifications, notifs are opt-in, not opt-out. I don't know if that's working correctly, so I actually am asking you all, for anybody who's new, are you getting notifications by default? Because I dislike notifications so much, and I prefer opt-in as much as possible. But anyways, so let me read, and that's my speculation for why Leo or somebody else doesn't join. I get it. Totally get it. Ooh, Zafarb, currently working on a math video about my progress going through a math book. That sounds cool. Let me add a to-do for that. I'm pretending as if I could Command F and find these everywhere to do. Thanks to Zafarb. My progress. I mean, that's what I'm trying to do. It's just very disjointed. It's extremely disjointed, and it's extremely, I don't know, inefficient, and just super inefficient. But I am showcasing me working through math books live, truly. Okay, so let's see. It almost covers it. The last optional subsection shows how the set of functions S to V, we got that, from a set S to a vector space V is also itself a vector space. Yeah, this is function spaces. Yeah, which is cool. The discussion right after example 7 shows how, for the special case, yes, I remember this example. For this special case, S is 1, 2, the set of functions S to V behaves like, ooh, okay, the Cartesian product V cross V. Ooh, okay. Did it exactly... I didn't... Ooh, okay, so that behaves like this. Let me figure out if I can, like, make that a little more formal or something. So we're saying that a function that takes two atoms, or, like in a lot of programming languages, we call atomic symbols like atoms. They can be numbers, but it's like even better to think of just like a generic, just like it's a symbol, colon A or colon B, and they don't have any mathematical properties. They're just an object. It's a thing. Two different objects or two different numbers, or like it makes sense to just use numbers in math, but anyways. All right, so we're saying from a function that takes 1 and 2, two separate objects, into V, I believe that the vector space of all such functions, that this is, I believe, isomorphic as vector spaces to V cross V. Behaves like. And that supposedly this is in example 7. Let me reread that and make sure that I understand where he says that is true, to make sure I'm not going to miss anything. So if I write it all out, what example 7 says, it's that example 7, f is a set of all real valued functions. Show that F is a vector space. This is the example that this whole discussion is stemming from. And yeah, we've been using this a lot throughout all of the linear algebra videos. Like, I really like that Fraleigh defines vector spaces and function spaces, like function spaces as a vector space, so early in the book compared to the other books that I've seen. And then the solution... Oh, wait, no. This one says, now let's consider the function space of all functions mapping a non-empty set. He doesn't require a finite non-empty set, so this could be any, which makes sense. I mean, yeah, this makes sense. Example, where is it? Example 3. Example 3 in Fraleigh is all functions mapping reals to reals show F is a vector space. I like to use v dot f or v dot s dot for vector space. And then what's cool is that in the proof of 7, it says that it's word for word exactly identical to as example 3. So removing the restriction that the domain is the real numbers and making the domain an arbitrary non-empty set, the same exact proof works. So I'm not going to write out the proof for example 3. We can take this as a as a given. But now we now indicate why we headed this discussion the universality of function spaces. Let S be 1, 2, so that F is a set of all functions mapping 1, 2 into R. Okay, so now we're back to what I was writing here. And then later he abbreviates or lifts that to V. Here's a cool comment. He says, let us abbreviate we're going to abbreviate the function f as of f1, f2. Okay, because there's only 2 points in the domain. I need to, I still need to see that this is okay. All right. So for example, -3, 8 is the function that maps -3 that maps 1 to -3 and 2 maps to 8. Okay? Yeah. In this way, we identify each vector A, B, and R squared. Okay, wait. All right, so in this way, we identify each vector A, B, and R squared with a function mapping 1, 2 into R. Okay, wait. So then we're saying for all A, B in the pairs of real numbers, we associate AB with a function which maps 1, 2 to the value. Yeah, okay, so for every AB, if I understand correctly, we identify each vector AB in R squared with a function f mapping 1, 2 into R, namely f1 equal A and f2 equal B. So then here, okay, and this is, it's an association, meaning I think each one pairs 1-to-1 with each other. So this is giving us, I believe, like a bijection. I don't know if I write the isomorphism symbol here or not, but this is a bijection with the function space, which maps R into R. So in Swift and some other languages, we write this as something like this. So R cross R is associated with functions that map, not R, but the two-element set. I want to write something like S2 or something, but that looks like the symmetric group. But here, even better. We could write it explicitly. So something like this, right? Then let's see. With a function mapping 1, 2 into R, namely f1 equal A, f2 equal B, if we view AB as a function f and CD as a function G, okay. If we view AB as a function f and CD as a function G, then we can define addition and scalar multiplication, can't we? Yeah, okay, thus the vector A plus B. Okay, yeah. Here, let's add a new page so I don't have to move everything else. Then, let's see. Then f plus g of 1 is defined as f of 1 plus g of 1, defining our vector or our function addition the same way as we usually do, and then this is a plus c. And similarly, RF. Well, same thing with the point 2. F plus G 2 is ... B plus D. Okay, that makes sense. And then similarly, we see the function, this is a super cool notation to me. I've never seen it before, but like bracket, or like, yeah, bracket RF, is it RF or RA? Yeah, RA, RB is equal to R times AB. Oh, dude, this is super cool. So the brackets mean that these are functions mapping 1, 2. So this is really similar to tuples in Swift, where tuples are not arrays of arbitrary length, but they have to be exactly 2 elements. Yeah, and 1 and 2, the numbers 1 and 2 kind of correspond to the indices of, yeah, the indices of this array or this tuple. Yeah, so we're really like kind of talking about tuples. We realize that we can equally well consider each vector of Rn as a function mapping 1 through n into R. For example, the vector blah 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 can be considered as a function blah 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 into R, blah blah blah. In a similar fashion, we can view the vector space MMN of matrices in example 1 as a vector space. So then Fraleigh defines similar associations of, say, 1 through 6, or associating with m by n matrices. For example, 2 by 3 matrices. Matrices labeled like A1, I think he writes it. A1, A2, A3, A4, A5, A6. So we have this kind of association from indices to matrices, and that it takes some more work or something, but we can also do the same thing with polynomials, where polynomials we I suppose are associating to each of this makes sense to me. This totally makes sense to me. Then we're associating the indices to, like, the way that we can represent a polynomial is by its coefficient, its coordinate vector, like, of the coefficients. And he also has a note that we view Pn as subspaces of P infinity in the following section. We make that precise or something. Yeah. And so then we get some things where all we need is addition. The definitions of f plus g and rf require addition and scalar multiplication in the codomain. For addition to be associative and commutative, we need the addition in the codomain to be associative and commutative. And for there to be a zero vector, we need an additive identity, 0 in the codomain, so that we'll have a zero constant function. It looks as though what we need is to have the codomain itself have a vector space structure. This is the case. S is a set, and V is a vector space, and the set F of all functions mapping S to V can be defined. Yeah, okay. So now I see, because I read these details a little more carefully, how Fraleigh has defined how a function mapping functions mapping 1, 2 into R correspond with R cross R, and then I think that Lockheed was then taking this later note, showing that V cross V behaves like or is similar to the set of functions mapping 1, 2 into a vector space. So yeah. I think I fully got that now. Let me catch up after. Yeah, apologize that I took some time and I was trying to figure it out on my own before peeking at chat. This seems to be a little simple, does it? Yeah, maybe. It might be. I'm pretty rusty. I'm 15 years away since I graduated from a math degree. So what's simple to some people is not simple to others. Like if you're learning it for the first time, this kind of stuff is not, simple for everybody. Cool. The book did it for R, but the idea translates to any V. I think I got there. I think I got to that point. After the solution paragraph, maybe I should have worded it better. No, you're good. You're good. Maps 1, 2 to R, not R to R. I think I fixed all those things. This part is walking you through how to translate the vector space structure on 1, 2 to R cross R. An ordered pair is basically just a tuple. I think I got most of these things. I don't know what all the retracted messages were. I wish that, I don't know if there's any, if people were like trolling or anything like that, just let me know and I'll ban people or whatever. Well, you deleted all your messages, so nobody can solve your problem and get $20 from you. Damn, and you're still able to solve it. Nice. I'm trying it. Just solve it on the beach? Give me a second. All right, hell yeah, dude. Work this problem with me. Like, everybody work this problem with me. I'll try not to give spoilers in the chat. I'm going to try my best not to read chat too much and take too many hints. I want to try to actually work this amazing exercise that Lockheed gave me in the Discord. By the way, shout outs to the Discord. Trying to build an amazing math community in there. All right. Yeah, I won't give more spoilers than what's in the rant. Yeah, sure. But anybody else who's working this exercise. Okay, I want to move this thing out of the way, I think. Oh, wait, no. I believe it's not showing up for you all. Okay, yeah, the side palette picker thing is not a problem. Okay, so let's see. I think I got that part. Translates to a vector space structure on V cross V. A mini exercise for you is to upgrade this to a vector space structure on the Cartesian product of two vector spaces, V cross W. Once you write the first step, you'll realize the rest is obvious. This is the direct product of vector spaces. Hell yeah, dude. Let's see. What can we get here? So, mini exercise is that everything previously was that V cross V is similar. And let me know if I shouldn't be writing the isomorphism symbol, but it's similar to the set of functions mapping 1, 2 into... Is there a problem with saying Z2 here? Any issues there? I feel like this makes sense. Z2, right? To I mean, Z2 is typically 0 and 1, but same thing, right? We just need any two objects. So V cross V is similar to the set of functions mapping Z2 to V. So V cross W is going to be similar to... Oh, wait. Tuples mapping to V cross W. And I think that the left-hand side should have a fancy X or something. Because here, like a tuple 0, 1... Oh, wait. Yeah, no, this works. Yeah, sorry, this isn't a tuple. This is a point, which is either 0 or 1. Right? And this is going to map to some lowercase v and some lowercase w related to the point 0. And this is going to map to some other point in v and w, lowercase v, lowercase w, right? And then this is the function. Yeah, we associate. So I think what we're saying here is that it's not related to or similar. It's like this is the definition of what the direct product of v and w is. It's the set of functions mapping 0 and 1 into tuples in v cross w. Right? Because this time around, is that right? Is this right? I mean, something feels a little odd that... No, this seems to make sense to me. But there seems to be some kind of asymmetry here, right? That in the first case it's V, and then in the second case it's V pairs. But yeah, okay, yeah. Which is where the idea that we were saying that the Cartesian product behaves like this thing. There's some weird... I feel like I'm onto something here, but it's a set of functions where every function is going to need to map yeah, 0 to... Is this the right thing? I think so. I'm just rewriting the second, like what I wrote below in a slightly different notation, but it's the same thing. Okay. Let me see it. Let me catch up. I feel like if you like to write this kind of stuff, consider blogging. Yeah, dude. Yeah, you absolutely could. You have a website where I rent out stuff, but not really a blog. The challenge about a blog is how do you get people to read your blog, right? Like, I feel like that's where showing up in communities like this one and like K Theories and Leo Lectures' community, like, that's my opinion. Like, it's hard to freaking get people to read a blog in the first place. So this time, you won't be making an isomorphism to a function space, but you can still construct a vector space structure based on what you have learned. Okay, so I shouldn't be using the isomorphism symbol, but we can define a vector space and we name it the left-hand side or something, right? A set of n labels is usually denoted bracket n or bracket n minus 1 if you include 0 to emphasize you're not considering it as a group or any extra structure. Hell yeah, dude. Okay. So, yeah, because I was thinking Z2 sounds like a group. Like we're considering usually Z2 means the additive group of two elements, right? And then, or Zn means additive group, and then Znx means the multiplicative group, right? Okay, so this is cool. Okay, so I haven't seen this notation, but I like it. Bracket 2, bracket 2. Hell yeah, that notation sounds pretty nice to me. Or just doing the set 0, the set 1, 2. Oh, this is a tensor product? Okay. This is where I like to really emphasize it. I'm going to be making mistakes. People shouldn't learn from me. But what do I feel like? Okay, tensor product is wrong. Okay. Nope, not this. Remember that the underlying set for V cross V was just the Cartesian product of sets. Based on what you know so far. Okay. Yeah, something feels off. Okay. So this isn't it. Okay, I think I need to rethink this again. Okay, so reminding myself. Oh yeah, because these are functions. Yeah, okay, so for all, like, I know that V doesn't have to be a finite dimensional vector space, but if V was finite dimensional, then V cross V behaves like I wanted to write F1 to Fn, but this doesn't seem right. So every function, F1 to Fn and G1 to Gn. No, it's not n of them. There's not n of them exactly. But I think that this... Okay, shoot. yeah, the bracket 2, like every function is going to map the tuple 0, 1 to a pair of elements, or, sorry. It's not a tuple. It's a function that's defined on 1 and 2. So I can define it piecewise and write 0. Shoot, I'm such a programmer, aren't I? 1 maps to V1 and 2 maps to V2. And that this is the same notation as bracket V1, V2. So bracket V1, V2 means the function that maps 1 to V1 and 2 to V2. The indices to the... Yeah, okay, so this is bracket, and that kind of reminds me of how, like in group theory and stuff, we write this type of notation to mean like a cycle. So this is a function which maps 1 to 2, 2 to 3, 3 to 1, for example. But this notation, the parentheses notation, means it's a function. And this bracket, we're saying that it's a function that maps the first index to the first value and the second index to the second value. Okay, so then how do I rebuild that when to have two different types or something? I guess we just need functions which map 0 maps to some element in V, and we need 1 to map to some element in W, right? Shoot. 1 and 2. Then I guess this maps to some kind of like V union W, right? Because we need all the elements of V and all the elements in W, and we need the input 1 to map to something and the input 2 to map to something. Yeah, this should be V union W, and then V union V is just V, so these definitions match each other. So now I think I fixed it, right? V cross W as a function space would need dependent function types to be properly made. What? Okay, those are too complicated for now, so ignore that. Hell yeah, dude, are you serious? Because I want to learn, I've always wanted to know what that's super cool. So to do dependent, this relates to dependent types. What? Really? That's cool. For now, you just need to focus on how you could add in a vector space structure on the Cartesian product of sets, following the example of Bro actually doing dependent function type. I suppose this does work. Not quite, because this allows both coordinates to be in the same space, for instance. Wait, what? Yeah, I was thinking that does seem a little wrong, because, yes, a function could be defining, allowing both to be of the same type, but we need a restriction that one must map to something in V and two must map to something in W. Like, we don't have this dependence, quote unquote, or something, that the second one... That's why I felt a little uneasy about this too. Yeah. Something... So it's like... I mean, this is why... I wanted to say that they're... So then, are these going to be pairs of functions? Because it sounds like I need... It sounds to me kind of like I need 1 to V, a pair of functions, 1 to V and 1 to W. Or something. Like V cross W or some behaves like, for whatever, I don't know if there's a symbol I should use here. Could you all give me a hint on that? Or should I just say V cross W is like pairs of functions which take 1 to V and 1 to W, right? Am I getting closer here? Why do we want this to be a function space? JC genuinely rediscovering a special case of dependent function types from scratch. Am I? Dude, you're giving me so much motivation here, because right now I would... If you weren't in the chat, I'd just be frustrated at the moment. Or I probably would have kept moving on earlier. I think JC took the equivalence of V cross V with the function space a bit too literally. I think I did. I think I did take that a little too literally. Okay, well, I'm just going to try to continue reading here. What you wrote up here. Because I think I'm starting to sort of see how I can... rewrite something like this. And then V cross W being like 1 cross right, this is very similar as a type to 2 points both mapping into V or something, I think. might be a good idea to keep thinking of direct product as multiplication of numbers and functions as exponentiation. So you're saying v cross v is v squared and v... Knowing the vector space structure on v cross w is a bit important for the rest of the rant, not just what it looks like. Okay, so the goal right now is v cross w as a vector space. But I shouldn't be defining it as a vector space in terms of function spaces, right? There's like some association to function spaces, but I can just try to analyze v cross w. Yeah, 1 to v cross 1 to w is the Cartesian product of sets v cross w, right? I mean, this is just another way to write like an implementation, or I mean, it really is equal, right? Or something like that. I don't know. I'm trying to see the way that we're... Do I need to be viewing do I need to be trying to understand this as function spaces? Or have I just taken something too literally here? Can I move on? I guess we have an overload of the X symbol. Yes. You don't need to write it as a function space. Okay, so I'm gonna try to move on, but like the function space discussion in the book is motivating this entire discussion, right? Because like you said in your hint that a mini exercise for you is to upgrade this to a vector space structure on the Cartesian product of two vector spaces, v cross w. Once you write the first step, you'll realize the rest is obvious. This is the direct product of vector spaces. Okay, so I want to write v cross w as a vector space. Well, so if we let a point be in... I switched to like some programmer notation. I mean, I don't see anything wrong with just defining the addition property as addition coordinate-wise, right? Like, I mean, this just feels like vector spaces Rn, and similarly k times vw is kv kw. We need I suppose... I don't know if I need a restriction that V and W are both vector spaces over the same field. I think so. But, I mean, a priori, they don't have to be. Right? Like, I could take V to be, I don't know, R2 over the real numbers. And W I could take to be C2 over the complex numbers or something. And then, or something stranger than that. Like I could take W to be polynomials, nth degree polynomials or something. And we have two different fields. So then how would we define scalar multiplication? I guess a scalar over V cross W would have to be a tuple of K1, K2 or something, dot VW being equal to K1 V K2 W, right? Where K1 and K2 are two different types. And the way I wrote this would, you know, W could be a polynomial or something. The Cartesian product of two fields is not a field, so this doesn't work. That's okay, right. That makes sense. This is not a vector space. Is there a way to define scalars over two incompatible vector spaces, like over two different fields? Okay, for a direct product, they do both need to be over the same field. So I need to assume that they're both over the same field. Okay. That makes sense. It's forced by scalar multiplication. Right. Okay, you must have them be the same field. Yeah, I felt like something does feel wrong here, and maybe if I continued, carefully checking the vector space axioms, I would have realized, oh, wait, then the pairs of two field elements, the Cartesian product of two fields is not itself a field. Okay, cool. So now, this is a perfectly fine definition. I can assume that it's the same field, and this, I believe, is going to fully define a vector space structure over V cross W. And it really behaves as you would expect, exactly the same as a vector space structure over R squared being R cross R. Okay, I think I'm somewhat caught up. I just don't see what the mini exercise... I don't see what you meant by upgrading the previous discussion to a vector space structure on the Cartesian product of two vector spaces. I feel, I could be wrong, I think I can just move on to the next part. Is that right, Lockheed? I'm going to also rename you over here Lockheed, or just Lock for short, I believe. So that when I say Lock, people know that the person typing here is the same as the person who wrote all this stuff here. Okay, I think I can just... but you're all good now. Okay, so the previous discussion only left you with a vector space structure on V cross V. Now you had to do it on V cross W. That was the upgrade. Okay. I guess... Okay. Yeah, I just don't see any reason that we need to connect that to function spaces. That we can define a vector space structure without function spaces, but there's this like association or something with function spaces, and then like mapping from one function space into... I don't know if I follow. I mean, at this point, there's two separate authors, so there's like slightly a different train of thought from the textbook author in this section versus what you were writing. But I think I sort of got this. Now the main meat. The above discussion constructed the direct product from the inside. You explicitly specified the elements and the vector space operations on the elements. Well, one thing is, at this point, you're talking about the direct product. And the direct product is not explicitly defined in this book. I wonder if it makes sense for me to read the definition of the direct product, which is not explicitly defined in this book, but it's at the very end of Axler. Like, would you recommend... Does the book define direct sums? It doesn't define direct sum or direct product. I kind of want, at this point, to write down the rigorous definition from Axler of the direct product and direct sum. Does that make sense? Like at this point, you're saying that I've defined direct product, and I think I'm still kind of missing what... Like, I'm missing, like, there's a gap for me. I suppose it would be worthwhile to read the definition from a book now that you've derived the main gist of it. Yeah. Like, I think that I kind of have some general idea, kind of, like, there's a missing connection in my mind about exactly how this connects directly to functions that you know about, and that you are kind of painting the picture of this correlation between the two, and saying that the direct product of vector spaces is hinted at, like almost covered, as you said, that the direct product of vector spaces is almost covered in this discussion about universality of function spaces. So this is definitely requiring a whole bunch of this book that I have not yet read, but let's see how much I can try to understand. I mean, there's a tensor products defined at the very end. Maybe that's what I was thinking of. Tensor product is defined at the very end, but we have direct sum. Is direct product just the same thing as direct as the Cartesian product? What is, because like this book doesn't have an index entry for direct product. It only has direct sum. And it actually shows up really early, 21. It's the tensor product that shows up at the very end. Is tensor product... Oh, direct product and direct sum are synonymous. Okay. Today I learned. Okay. I thought that these were separate ideas. Okay. Okay, hell yeah. Well, okay, this is kind of more like what I thought, what I was thinking of. Direct sum... Direct sum feels very different. I thought products can be completely different types, whereas direct sum... No, I remember this. No, I think I remember this. Okay, the infinite case is looking at you right now. Okay, so, yeah, let's write this out clearly from Axler, which... I do remember, and I think I would have guessed this or really gotten it pretty dang close, if not totally correct. I think that there's a couple of little technicalities that I would have missed. But Axler definition 1.41 on the direct sum plus. Suppose V1 through Vm are subspaces of V. So I was totally wrong. This is early in the book. Tensor product shows up late in the book. And I believe, if I remember correctly, tensor products is how this whole discussion started. Like we were talking about tensor products came up on stream. So at least here, Axler defines on subspaces, which is where I feel that there's something missing comparing to arbitrary two separate vector spaces. The sum v1 plus ... plus vm is called a direct sum if each element of capital V1 to capital VM can be written in only one way as a sum V1 plus ... VM, where each VK is in capital VK. Okay. So I was going to say that they're disjoint, but they can't be disjoint because they all have to contain the zero vector. the zero needs to be in every. Ooh, Zafar, your video's up. Hell yeah. Mr. Beast hits 500 million. Okay. Axler's defining an internal direct sum. Okay. Locke points out that this is an internal direct sum. Interesting. If V1 plus ... plus Vm is a direct sum, then capital V1 plus ... Vm denotes V1 no circles sum to Vm with the with the plus circle notation serving as an indication okay. Hell yeah. So the direct sum, that the sum is called a direct sum if each element of it can be written in only one way as a sum v1 plus ... vm. So one result of this that you can prove is that or in other words, VI intersect for any two distinct subspaces. I believe that this is the trivial subspace. Ooh. Yeah, this is not the direct sum of arbitrary vector spaces. World's first case where Wikipedia might have been more helpful than a textbook. I don't know. Wikipedia's relatively fine for math. It's okay, but it's a reference. Yeah, I feel you should not use Wikipedia as a textbook. It's super, I think, important to follow one author's presentation and their guiding. They're like, Axler is like hiding some information from us as lowly, linear algebra 2 students. But then, yes, we can extend this to more complex spaces or something. But I bet that direct sum later, because direct sum shows up in page 21, 42, and 98. So I think that Axler then defines it for arbitrary vector spaces next. Let's find out. Every subspace of V is part of a direct sum equal to V. No. Okay, so that's about bases. I wonder if maybe it's an exercise. Man, I need to do some Axler. This is really pretty. I need to work some of these. It doesn't look like it's defined in an exercise either. But there's 3 different places where there's like a top level definition, or like direct sum. Yeah, direct sum is defined on 21, 42, and 98. 98, do we get a more general definition? No, these are... Yeah, for Axler, everything is a direct sum of subspaces, from what I can tell. Oh wait, definition 387 on page 96. Thank you, dude. Okay, so that's just 2 pages earlier. Okay, okay, in the index. Okay, in the index he didn't call it a direct product, so I wasn't seeing product. But I was on the page after this. And I saw the word products, and I was starting to think, I think that this looks kind of similar to what we're talking about. Like, this theorem or result or something on 3.93. That looks somewhat similar to what we're talking about. Okay, so definition 387. Let's write that out. Okay. Hell yeah. Feel like I'm supposed to shill for Leo's textbook right now? Okay. Leo's first chapter would spoil the entire exercise. Yeah. Dude, I don't know if we're gonna get to the meat of this exercise today. I'm just still in like the first baby steps before we even got to the meat. But oh well, I'm trying my best here. Axler definition 3.87, product of vector spaces. Here we go. So product is synonymous with direct product for vector spaces, right? Suppose V1 through Vm are... Okay, here we go. Are vector spaces over the same field. So we had this requirement that I was discovering, I think. The product V1 cross Vm is defined by V1 cross ... Vm, which is a set of tuples, as I expect. He doesn't use Vi and Vi, but that, yeah. Same thing. Addition is as expected. Yeah, and then multiplication is as expected. Okay, so this is not really very illuminating. It's just like more formally written. Okay, scalar multiplication is defined as... dude, I don't like that he uses lambda. I mean, isn't lambda always used for eigenvalues? Is this part of Axler? Wait, no. I mean, Axler loves eigenvalues. He doesn't like determinants, right? I don't like that he uses lambda for his scalar multiplications. But, like, I prefer K. Okay, so this is exactly as I was expecting. It's tuples, and addition is defined as you expect, and scalar multiplication is defined as you expect. But now I'm more confident that there's nothing missing to me, and that, yeah, you can show that this forms a vector space as you would expect, requiring that they're all over the same field. Okay, nothing surprising here. Lambda, lambda, lambda. Yeah. Gotta take baby steps to take bigger steps. Okay, kind of the point is that the vector space structure is for/obvious when you try writing it down. Okay, technically you'd have to show additive inverses and the zero vector and such, but yeah. I was like, you have to, like, it's not just addition and scalar multiplication, but that this does force. Okay, here we go. So that this might be going toward the direction that this is the only way to define a vector space over M vector spaces. Like, I wonder if that might be where this is going, like universality and a universal property. Like, I wonder if this is the only way you can define, because it is forced by the... No, I mean, it couldn't. Like, it's not the only way you could define addition to be trivial. Like, all of them like, addition maps to 0, and multiplication maps to 0 or something. But if you preserve addition in the original vector spaces and scalar multiplication, yeah, no, it can't be the only way you construct a vector space. You're kind of getting to the point. There's a reason why it is forced. I think that I mean, what would be wrong? Like, do you have to just stipulate that the only, like, other than the trivial vector space or something? Like, because I could redefine addition to be mapping everything to 0, and 0, is an element of every vector space. Like, they're different zeros, potentially, but, right? Dimension of a product is the sum of dimensions. I wonder if products and direct sums Once you discover the universal property of direct products later on in the rant, you could try to show why the trivial structure will not specify that universal property, will not satisfy it. I see. Okay. Sweet. All right, so I think I'm ready to read for sure now more. So, yes, the vector space structure is exactly as I would have expected it to be on the Cartesian product of two vector spaces. That makes sense. Okay, so I'm ready to keep going. The main meat. The above discussion constructed the direct product from the inside. You explicitly specified elements and the vector space operations on the elements. Yeah. Now the challenge is to construct it from the outside. So previously we defined addition and scalar multiplication by referring to specific elements and defining it using points. Now we are seeing if we can construct the same from the outside. Find some property P. So the goal that you're giving me is to find a property, right, of vector spaces which has the following conditions. The old direct product is called the Cartesian product to avoid confusion. So I want to see if there's I think what you're saying is if I have two vector spaces, I can construct a new vector space V cross W, which is the Cartesian product, and that this is a vector space. And now we're trying to see if we can find another vector space, if I understand. And I'm going to give this symbol. Like, is there another way to generate a new vector space from 2? Okay. And we're looking for a property of vector spaces with these conditions. The old direct product is called the Cartesian product to avoid confusion. So, like, this is the original, canonical direct product, and we're looking for... I think you're saying that a priori there might be another way to build something that we could call the direct product, or the product, like a vector space from two vector spaces. A priori, that there might be a way to do that. So I'm looking for some property about vector spaces that already exists that satisfies 3 conditions. A vector space with property P behaves like the Cartesian product. Let's see. Let's get a new... Well, I think I have enough space right now. Okay, so... a vector space... with property P behaves like... which I'm going to make up a new symbol. W behaves like the Cartesian... Oh, wait, no. I'm already using W for my second vector space, right? I'll call this V square X W. I don't know if square X is a thing, but... Or why don't I call this VW? Maybe. VW is some new vector space, and it somehow behaves like the Cartesian product. And behaves like is justified soon, so I will trust that. Given two vector spaces u1 and u2, both satisfying property P, u1 and u2 are the same. The correct notion of sameness of vector spaces is isomorphism. Okay, so we have some property which will force any two vector spaces u1, if P is true for u1 and P is true for u2, then u1 has to be isomorphic to u2. Isomorphism of vector spaces means that there's a bijective homomorphism which respects addition and scalar multiplication, like the two operations. The algebraic structures of the two. I think your line of thought right now is exactly what Locke was aiming for. Okay, cool. I don't know exactly which comment I made, but I think I'm on the same page now. To give some context, now the challenge is we're trying to characterize what properties a direct product has that makes its vector space structure so natural. Okay, yes, you're thinking exactly right. It would be better to read points 2 and 3 to understand why you wrote part 1. Wait. VW, also known as the triple U. Okay. Yeah, it does look like a triple U. VW triple U. That's like the... Anybody here, this is a little detour, right? But like, anybody here watch the movie The Vavitch? That reminds me for a second of The Vavitch. Anybody know what movie I'm talking about there? It's just a stylized way to write The Witch. Great movie. But yeah, so this is like the triple U. Okay, so we're looking for some new vector space. And we're looking for a property about vector spaces that forces any two vector spaces with that property. Are those subspaces or... Wait. Given two vector spaces both satisfying property P, u1 and u2 are the same. Recall that the correct notion of sameness of vector spaces is isomorphism. And I think I think I know what isomorphism of vector spaces is. So then it can't be okay. So certainly the property needs to include the fact that, like, one fact that I feel confident about, if I start writing properties about this universal property, which I think is, I already know the word is universal property. If u1 and u2 both have the same property, then u1 is isomorphic to u2. We certainly need that the dimension of u1 equals the dimension of u2. Like, I believe that we need them to have the same cardinality, the same size, because otherwise it can't be isomorphic. And I think, do we need, our vector spaces to be finite dimensional? Possibly. I think... Because I think that the real numbers as a vector space are not isomorphic to the complex numbers, right? But, well, I guess if they're over... Yeah, certainly. Because you can view the complex numbers as a vector space over the real numbers, and you can view the real numbers as a vector space over the real numbers, but there's no way that those two are isomorphic. So... in this case, if the complex numbers are viewed as a vector space over the real numbers, then the dimension of the real numbers is 1, and the dimension of the complex numbers over the reals is 2. C is isomorphic to the plane, I believe, over the reals, but it's isomorphic to... Like, the dimension of C, I believe, is 2 when viewed over the... as a... Yeah, like, the basis of C is the span of two vectors, 1 and I, when viewed over the field of real numbers, but it's the span of 1 when viewed over the complex scalars. So over so this feels to me like something that our property P needs to include, because otherwise the two vector spaces wouldn't be isomorphic, I think. So the fact that property P implies that the two are isomorphic, I believe that we need the two vector spaces to be the same dimension over maybe isomorphic fields. Because, like, I bet that you could have two vector spaces with... I think that they don't need to have the same field for the two vector spaces to be isomorphic. So I bet F1 needs to be isomorphic to F2, and U1 and U2 have to have the same dimension. That's my thought right now. I'm gonna keep going because I feel like I'm on a good train of thought at the moment, and then I'm gonna read chat. I feel that that's important. I don't know if that's enough. The Cartesian product V cross W satisfies property P. Okay, so the Cartesian product satisfies property P. It's a property of vector spaces which has the following conditions. Cartesian product satisfies property P. The Cartesian product, the dimension of the Cartesian product is the sum of the dimensions, I believe, of the two vector spaces. Is that right? I think I saw a theorem that looked something like that on the next page in Axler. And I believe that that would be true. The dimension of... Yeah. So I'm a little confused on what the statement of property P would be given two vector spaces U1, because like the type of the property feels like really different. Cartesian product V cross W satisfies property P. This justifies property 1 in combination with property 2. A vector space with property P behaves like the Cartesian product V cross W. Yes. So any two... Oh, I see. Okay. A vector space with property P behaves like the Cartesian product V cross W because a vector space... Any two vector spaces with the same property have to be isomorphic, and so then bullet point 1 is saying that a vector space with that property is isomorphic to the Cartesian product. And the Cartesian product has to satisfy the property. Like, the claim is, like, I want to find a property where the the Cartesian product does satisfy this, and then anything else must be isomorphic to it. I feel like it's for any alternative direct product that the dimension of the product equals the sum of dimensions. That is my guess right now. From the outside means you are not allowed to refer to elements inside vector spaces now. Hint on how to do this. The solution is... Okay, let me read the hint. Give me 1 second. Let's go to Hawaii for a second. Let me just read this hint and make sure I don't dox myself in the process. Okay. Everything's good. Let's get the Discord back up. Let me find that comment and read that hint. The iPad might get all messed up. Yeah, the cropping of the iPad is a little funny. Let me see if I can... I should really create a new... Let's get a new... Which one is this thing? It's a... Let's duplicate this. I just want to make sure I can get the entire discussion visible. without messing up my tweet. This version of the window is cropped for notability, whereas this version is better cropped for this hand. So let me read this. So I mean, certainly what I just talked about is not referring to any individual elements. It's not defining anything from the inside. It's only speaking of the outside, I think, as long as we say that the dimension of the basis is not referring to the individual elements, but the size of the basis. I think that I'm on the right track here. Activate your functional programming brain. Linear transformations are your best friend. Okay. Linear transformations are your best friend. Okay. Okay, I saw briefly some comment about, and I'm not going to. Okay, now I think we're getting to the. I briefly read this next theorem or something in Axler, and I saw that he was talking about functions. I think that now we need some kind of. Okay. I was not. What I said earlier was incomplete for sure. So you said here. Activate your functional programming brain. And we need linear transformation. So I think I need something about properties of linear transformations. Okay. So, okay, I'm going to read chat now to catch up, but I think, all right, not subspaces, just any two vector spaces. Finite dimensional doesn't matter, but if you want to stay sane, you can assume it. What you're studying, kind of like some hints toward discovering category theory in context. Like truly category theory in context of linear algebra, right? I tried reading this book years and years ago, and it kind of hurt my brain. But now I think that I'm actually learning some real category theory in context of linear algebra, which is super cool. All vector spaces under discussion must be over the same field, otherwise stuff becomes ill-defined. Okay, thank you. Isomorphic fields are basically the same anyways. Okay, I could spell out why it justifies property 1. I think I got it eventually, right? Keep in mind that dimension is not the only invariant you have to check. Yeah, I'm seeing that there's something more. I believe that property 1, just the fact that I mean, I was wondering if, if dimension of V equals dimension of W, and both V and W are over the same field, I thought that this would imply V is isomorphic to W. Are you saying that this is false? I guess I can try to prove this for myself or disprove it, but why wouldn't it? I mean, in the examples I have in mind, I thought that it would be true, but maybe not. The complex numbers being seen as the span. Well, this would be like a subset, wouldn't it? Oh, wait, I was trying to do something like the span of I over the real numbers. And then I was going to try to multiply I times I to get something outside, but that doesn't work. I mean, I do think that this is isomorphic to the real numbers over the real numbers. I mean, it's just, yeah, like if you add any two, like it's just a relabeling of the axis of the number line where every number now just has I labeled with it. Something with polynomials, or I think that this is true. Let me read the chat. Cat, yeah, she is, she's trying to study, sorta, kinda. Okay. I could spell out why it justifies property 1. Keep in mind that dimension is not the only invariant you'd have to check. Cats are built for category theory, so it's obviously interested. Cat theory, yeah. It would be nice to first analyze the properties of the Cartesian product itself, since it would be hard to come up with such a property out of thin air. Okay. Here's where I think that we start drawing some nice little diagrams, right? Like, I can like embed V into V cross W. And I can also embed W into V cross W. Then I think that this needs to, let's see, can I go both directions then? Yeah, because I can embed and I can project V into V cross W. Likewise there. So then that gives rise to another map, right? Because I can... Like first, I don't know the right word for this, but like I can project V cross W to V, and then the inverse is like an embedding, right? And likewise, so then this gives rise to a map from V to W, defined as the composition of, so if this is pi v and pi v and pi w, let me know if there's a better name or something here. Then phi mapping V to W would be taking the embedding, the projection of W after the embedding of V or something. And that gives us phi and phi inverse. And I bet that there's some nicer names or something for all this. But yeah, I think that this is giving rise to a map between V and W. So I can kind of like, and that's what a linear transformation is, exactly. Back to the activate your functional programming brain and composing, maybe what you meant by that hint was just composing functions in functional programming. But then if I have well, if I want this to be like invertible, then I would need to map from V to I would embed an element V to the kind of like function space to that function space which takes V into W. Right? Because I need to, if I want V and W to be isomorphic, well, I don't know if they're isomorphic. No. Because yeah, like mapping a point in vector space V into, like, this wouldn't map into V cross W. Yeah, there's like another object in this, I think, to complete the train of thought that I'm thinking of. But like this maps to some V and some W corresponding to V, which is like could be seen as a function from V to W. But yeah, there's every element. If I embed V into V cross W, it's like we map a point to like every possible if I want to embed V into W, we could take any of the elements of capital W as the second argument. So, because I can map to because I can take any element of W as the second argument, it's kind of like we are mapping V to a transformation corresponding to V. And again, this is, you said linear transformations are your friend. Which sounds like what I'm talking about here. So with this diagram, once I choose, if I choose a transformation between T and W, I don't know if I know that it needs to be invertible, but once I choose a transformation from V to W, then that, I guess, gives rise or something to this embedding that I'm referring to. Is that... And we certainly have the projection from V cross W to V. I think something like this is along the right direction. So we're not actually mapping V to V cross W, but we're mapping V to V cross linear transformations from V to W. And then from that, I can go to V cross W. Right? Like this, I think, is making my thought a little more concrete. This defines like an embedding. As long as I choose any, like for V mapping into V cross L VW, I would need to select one of those transformations in order to complete this diagram or something. I don't know, dude. Let me read chat. I feel like I'm getting closer here. I think that I don't know if I have enough to complete the thought right now. The solution is spoiler tags are broken into segments so you can use them as hints. Hell yeah. It's also written in conversational style to help you ponder. I will also assume you have finished the Cartesian product construction mini exercise. So I think I've done that. You said activate functional programming brain. Linear transformations are your friend. That's what you said in this spoiler tag. Okay. Hell yeah, dude. Hell yeah. We're back at Notability now. Oh, well. Let's go back to Discord. It keeps leaving RAM. Okay, I'm gonna thank you for breaking this up into separate hints so that I can, because I feel like I'm on like some train of thought that's like, somewhat similar to the section of Fraleigh that sparks this discussion that you're relating this to. And now I want to see if maybe this first hint, if I can try to continue the train of thought. I think it's incomplete. Like, I'm not done. I haven't like found the universal property, unless it's like some universal property saying that that there's only one linear transformation that I can choose or something. Like if I want to it's a property that makes V and W isomorphic, right? Okay. So I feel like I haven't yet said that with some property P, then V and W are isomorphic. So, V and W are isomorphic, so we have T and T inverse. Given some property, then V and W are isomorphic. So, the set of linear transformations from V to W is defined, and so is the set of transformations from W to V. So because V and W must be isomorphic, I could go from V to W to V cross W. Because they must be isomorphic, then V maps to W, V maps to, right? Like there's like one corresponding W for every lowercase v, and then this maps to if our isomorphism is phi, then from a W we can... Is this what a pullback is? Pull back to V? Or something? like that seems like a good place to use the word pullback, which I've heard of before. I've never really studied category theory before, but this seems like that's what it's doing right now. Like, if I have an isomorphism between V and W, this is now giving me this unique embedding into V cross W. I'm going to call it embedding E, because I don't know any better. So this... like, even though we've lost V in the process, like the fact that we have an isomorphism between V and W, we can like reconstruct V in this bit. I feel like I'm onto something now. Okay, so let's go back again to the hints. Discord keeps getting evicted. Annoying. Hint, activate your functional programming brain. The direct... okay, wait. The solution is, it's also written in a conversational style to help you ponder. I will also assume you finished the Cartesian product construction mini exercise. I think I did that. The direct product of V and W is some vector space U. The strategy we take is to find some way to characterize all linear transformations into U. How does this characterize U up to sameness / isomorphism, you may ask? Okay, right now, at this point, I'm going to peek at chat and see if I'm, like, way off. Oh, a typical embedding symbol is iota. Yes, I have seen that. Now that you mention it, I have seen that before. Thank you, dude. Fancy mathematicians confusing people with these little curly dotless eyes. Okay, thank you. Let me read exactly. Yes, hee hee. I'm glad that I'm sort of following along. Alright, so the triple U, finite dimensional doesn't matter. Isomorphic fields are basically the same. Justified. Let me catch up. Where were we? Cat theory. You might have been saying yes, hee hee, at cat theory. I don't know. It would be nice to first analyze the properties of the Cartesian product itself. V and W are isomorphic for finite dimensions. Right, if they have the same dimension and the same field, I think is what you were referring to. That's why I say, if you want to stay sane, you could limit yourself to finite dimensions. Okay. Note that isomorphism of vector spaces is only defined over the same field. Okay. Oh no, the same coproduct curse that cursed me is also cursing JC. Uh-oh. What's the coproduct curse? I fell into the exact trap during the write-up. Note that this map, V to W you have, is very simple. If you write out the elements, I might have fixed that part, because I know that I was really changing some bits a lot. And, like, corrected myself. Let me pop out chat better. Okay, you will not mention the coproduct curse spoilers. Hell yeah. Okay. Note that this map V to W you have is very simple. If you write out the elements, your line of reasoning would show that any two vector spaces are isomorphic. Yeah, certainly yeah, something felt wrong earlier. I was like, this would show any two vector spaces are isomorphic. That's not right. But it's more that if we assume that the two are isomorphic, then this gives rise to like a unique embedding into the Cartesian product, right? You should use the fact that the linear maps involved are linear. That will maybe show you what the explicit description of the map involved is. Not quite any element, somewhat closer. One thing you should really check is if WV really is allowed to be arbitrary. I think it's not. Okay, since we're dealing with linear maps, not arbitrary functions. So I need linearity somewhere here. Property 2 is what you want to try to look at with that first hint. I will not mention the coproduct curse spoilers. Okay. 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 All right, so I'm caught up with the hints, and I see that there's something I'm missing. We need linearity. So WV, you're saying, is not arbitrary. There's some restriction to what WV is allowed to be. I love that I'm just like showing a bunch of wrong math on the internet. So if somebody wants to learn category theory, dude, this probably is not the best stream to do it. Or maybe it's a good one. I don't know, because maybe you can actively mistrust everything that's on screen. Like, and you can actively, if somebody else is trying to learn category theory for the first time, you can be more active in catching where I'm going wrong and try to solve this problem yourself, you know? Because I feel like something is a little funny about what I've written right now. Something feels a little funny. I can have Discord up on the computer so I can like peek again at the conversational style. I promise I won't click anything I haven't clicked yet on the iPad. The direct product of V and W is some vector space U. The strategy we take is to find some way to characterize all linear transformations into U. Yeah, characterize all linear transformations into U. Okay. I like your notation, so the direct product of V and W is some vector space U. So I have V and I have W. And then I want to combine V and W into some other vector space U. I want to smash those together as a product into U. And U needs to be a vector space. All of them need to be vector spaces. over the same field. The left side of the notes is slightly cut off. Oh, yes. Let's go back to... Thank you. Thank you. Apologies. We need to go back to the iPad, or Notability view. All right. Here we go. Thank you. So... V and W are both vector spaces. And we want to construct a new vector space. Does that mean... Well, from any vector space to a new... Like, if U was a vector space, then we would have to have a linear transformation from V to U, and we would have to have linear transformations, the set of linear transformations from W to U. Whatever V and W are, assuming that U is some new combined vector space, then that generates the new vector space of linear transformations. What are properties about linear transformations that we need? We need things like 0 maps to 0. That's one fact that we have to have. We have to have... So 0 in V maps to 0 in U. 0 in U has to map to 0 in... Oh, wait, sorry. 0 in W has to map to 0 in U as well. Did we get some correspondence of transformations? And am I allowed at this point to assume that V and W are isomorphic? You said that the property P says that if property of V1 if V1 holds this property and V2 holds that property, then what was it? Then the Cartesian product holds the property, or then it behaves like V1 and V2 are isomorphic. Wasn't that it? That was it. So the only thing I can think of right now is that if they're over the same field and they have the same dimension, I think that implies that V1 is isomorphic to V2, right? Yeah, it's in the Discord. By the way, join the Discord, bro. All my notifications are opt-in instead of opt-out because I hate notifications. Unless, absolutely necessary. This is in... My Discord is a blend of a little math folder as well as music. I've got a lot more music stuff in it, but I really do want to build up this math folder. We've got #math, which is where this little written up exercise is. And I also want to start doing a math hang soon. And then here's where I'm announcing all my streams. So you can get going live notifications if you want. Okay, right. I can't assume that V and W are isomorphic. Okay. But I want a property that would imply that two vector spaces with this property implies that the two vector spaces are isomorphic. Yeah, those are like separate things, right? Here, I can't assume that these two are isomorphic. Let me read. Linear algebra category theory exercise. In the Discord, I will give a bit of a hint here. Projection maps are better to examine than the embedding maps for your case. Not that embedding maps don't work. They take you down a different rabbit hole. Also, you can't assume V and W are isomorphic here. Okay, so you're saying it's better to go the other direction. We are... Okay. Thank you. Thank you for the hint. You're saying that instead of going into embedding maps, it's certain... Okay, I see. We want two arbitrary vector spaces to define a third vector space, U. And we're trying to find some universality that shows that U must be V cross W when something is true. Is that accurate? Is that correct? Like, so is this direction, if I'm taking the arrows in this direction, then I have something called the coproduct or something? Like, is this the coproduct curse somehow? The rabbit hole that this would lead down? So if I start from the other direction, assume that V and W defines a third vector space U, then U we can project to V, and we can also project U to W. Maybe pi 1 and pi 2, or pi W, pi V, or something. Um, yeah, I mean, we can always build linear transformations from any two vector spaces. And linearity implies things like 0 maps to 0. What else do we need? We need associativity. Wait, I could try to write out my vector space axioms. Addition, scalar multiplication, addition property. There's the way I've learned it and memorized it is that you need to define addition and multiplication on a vector space and a field satisfying associativity. Got to start with ass. We need identities. The existence of additive identity, and the equivalent over here is, well, the existence of the existence of one is implied by like the field, that there's a multiplicative identity in the field, but then we need a multiplicative identity like 1 times any vector needs to be a scalar multiplicative identity, right? We need commutativity of addition, and we need additive inverses, right? And then we need 2 different distributive properties. I think of this as distributivity with 2 vectors, and then distributivity of 2 scalars. Or K and L, maybe. These are our vector space axioms. And from those, we derive some results like 0 must map to 0. I feel like using multiplicative identity is something that we could use because 1 exists in the field for the same field that both of these are vector spaces over. So is that something that we could use here somehow? Do I know... Is the property something like that this must be unique? That there's only one? Because, like, what I'm trying to figure out is... What I'm trying to figure out is why can't I define multiple different projections into W and V? And I wonder if this, like, maybe you can't say that a priori, but maybe this is the universal property that I'm looking for, that there is only one projection from U to W and from U to V, so that there's only one projection to both of them. Which then means that that defines uniquely pi V pi W map to V cross W. Is this what I want? This is starting to look like a complete nice little category theoretic, you know, commutative square kind of thing. Or maybe it's... Maybe this is the universal property. Well, wait. I guess there being one... If this is unique, then it gives rise to pi W and pi V, right? If this... We want... Oh, shoot. Let me read. Okay, now I feel a little more, a little better because Zafarb just said, I just read the exercise and its solution. Holy crap, what a hard exercise. Maybe it's because I'm still a baby. This is super awesome, man. Thank you so much for writing up this. I should put big question marks everywhere so that if somebody's scrubbing this video, they're not just like, dude, that is wrong, it's almost right, but you know, this is wrong math. I should put question marks everywhere so that somebody visually sees that this is, don't take notes from me. I don't know what I'm doing right now. Also, you can't assume V and W are isomorphic. Coproduct works, but it answers a different direction. Yes, this leads you to the universal property of the coproduct, which is not what we're looking for. The stream would go on for far too long in that direction, so I had to take you out. You have the basic idea here. Try to look at the first hint you clicked on after the FP1, now that you have this projection diagram. Yeah, because I keep starting to read the hint, and then I'm like, that sparks a thought, and then I want to come over here and try to see if I can make a little more progress. So let me look at the hint again. Don't hesitate to put in U equals Cartesian product and look at elements to get down to earth things to look at. Okay. It's easier if you have the relevant linear algebra background. Yeah, the hints were very nice. I can't imagine how much time that took. Also, you have a great exposition lock. That isn't it. V cross W has a whole natural number worth of maps into V. Damn, you are really close already. Oh my god, I really had to go out at this exact moment. I'll see if I can squeeze in time. Gonna dip for a few minutes. Okay, I think I'm getting close. I'm sorry that it sounds like you had to step out when I'm getting very close here. And you were correcting me on something I was writing earlier. Dang. Well, I'm sorry that you had to dip. This stream is going on very, very long. We might have to continue it. Dude, it's already been 3 hours, bro. I feel like I should force these streams to not go on for more than 3 hours. 3 hours, like, we're making progress, but 3 hours a day of math is like more than enough, way more than enough for my purposes of learning math right now. But I think that we're getting somewhere, and I'm just gonna freaking continue this tomorrow as a part 2, trying to understand something like I think that this is something like, I think that there's one map into the Cartesian product or something. Like, okay, dude, I think I'm QED, nicely done, to be continued. Yeah, hey, what's up, Sandeep? What's up, Vob Edits? Yeah, I think now's a good time to call it for today. To be continued, dude. And I'm going to try to promise I'm going to promise to try my hardest not to peek and look at any hints and try to see if we can figure this out on stream together. Because I know, like, I'm trying to work this amazing exercise and exposition that Lockheed wrote up in the Discord. By the way, shout outs again to the Discord, y'all. Link in the description, link in bio, or just type this into your browser. He has a really nice exposition trying to lead me to category theory, which is a beautiful abstract form of math that I never really learned. And it's cool to see, truly, category theory in context of something I've seen in linear algebra. I haven't seen this either. This is kind of like the next step after linear algebra or something. Okay, so let me write out what the spoiler tag said. The direct product of V and W is some vector space U. So I think I just saw that, and then I started going off into some new ideas. The strategy we take is to find some way to characterize all linear transformations into U. The strat is some way to characterize all lin trans into U. Okay, linear transformations into U. So then I guess it goes the other direction or something, like maybe. Oh, that's like the co-product, right? So then V cross W projects to W, and then W mapping into U. So maybe the square looks just slightly different. It's more like V cross W to V and to W. In that we want to characterize all linear transformations into U. So this was like what I was finding earlier and thinking about, like a point W mapping to U. We can do that by mapping W to, like, a point W maps to W and a linear transformation corresponding to W where okay, wait. So this is going to map to a function which takes the point W and returns some other V. I think. But we don't know. Wait, let me reread. The strategy we take is to characterize some way to characterize all linear transformations into U. How does this characterize U up to sameness / isomorphism, you may ask? Okay. Oops. Yeah, I'm confusing myself. Okay. So, the direct product of V U is some U. How do we characterize all linear transformations into U? How does this characterize U up to sameness / isomorphism? I'll just say ISO. And then this next bit is also hidden by a spoiler tag. Ah, dude. What's this? I'm trying to learn a little bit about category theory. This is an exercise that Lockheed SR71 Blackbird 127 gave me in my Discord. And I'm trying to figure this out. I feel like if I try to give this some thought privately off camera, just quietly, privately off camera, I might be able to make some more progress. So I might try to work a little further, but maybe my rule that I set for myself is that I don't look at any more of the spoiler tags or something. Maybe I try to see how much farther I can get without looking at more spoiler tags and without looking at any books. Yeah. Dude, thanks everybody. I had a blast today. I want to stick around until Locke can make it back, just to say thanks and everything. He said that he'll be in and out right now. I mean, it's been like freaking 3 hour stream today. That's more than enough. That's more than I should be doing. That's more than I should be practicing math, as a hobby. I kind of want to continue this as a part 2 tomorrow, but I feel like we are getting somewhere here, and I'm starting to see a place where context, like a context where category theory is coming up. Yeah. Thanks everybody. Okay. You said, how do we do this? You might ask. I'm going to peek a little bit more. I want to keep working until Lockheed comes back. So let's see. That might mean that we have to keep going. Let's keep going just a little bit more. Okay. Well, say you have 2 candidates for the direct product U1 and U2. Okay, so here's the next spoiler tag. Say you have 2 candidates, U1 and U2. Are we live? Yeah, we are still live. Thought stream ended. Nope. You're done with representation theory already? No, I have solved exactly 1 exercise. Bro, yeah, I was about to end stream earlier, but I wanted to make sure that you, that I caught you at the end here. Okay. All right. Well, thanks, dude. I do think I'm going to save this next part for tomorrow. What do you think, Locke, I wanted to ask you before I sign off. First off, thank you again, bro. I really freaking appreciate this, this amazing write-up in the Discord. I freaking appreciate it, dude. This is an opportunity where doing like a math hang would be really fun, like being able to give each other problems like this and stuff. So yeah, representation theory, Hyrule, I don't know if you know, but we are doing a spiral structure. So just yesterday, I just finished this cycle, this spiral through representation theory. I did 3 streams. So coming up next, we're going to do, I'll just say C4, 4 calculus, 10 linear algebra streams, and then we're going to do 4 representation theory streams, and then we'll do 5 calculus, 5 calculus, 10 linear algebra, 5 representation theory. So, it's about time. We just finished 3 representation theory. So now today we're on an off-topic special stream. So Locke, I just want to know what is your thoughts. I want to do another stream, another special stream, trying to continue this. Do you recommend to work this exercise for me to try? Dude, I don't know if I can justify spending more time privately myself. I just don't know if I'm going to have the time for it because I've already done 3 hours of math today. Like, do you think it's better for me to keep chewing on this problem privately on my own over the next couple of weeks and then come back to this after the next cycle? Or try to continue live tomorrow? Oh, shoot. And also tomorrow I'm not available. Tomorrow I'm out of town. It would have to be Monday or Sunday night. But, like, do you think that I should try to chew on this privately or just continue on stream? The hints will look a bit disconnected from what you have, but don't be scared of that. Yeah, I won't be scared. Dude, this is awesome, man. I really appreciate this this exercise. I appreciate it. Like, yeah. I think that this is kind of a cool approach. Like, I'm trying to learn math and share, like, how to learn, trying, like, this is a kind of a cool, almost like a genetic approach or something to math, like trying to derive some of this stuff rather than going straight to the book and trying to understand after reading the definition. Like, this is more like kind of trying to discover this idea, like the way that you have it written up, like the way that this is written as an exercise, like a guided approach toward learning about this idea. I think it would be better for you to have a think about what you have done so far before you move on. Okay, I'm going to try to think about it. I don't know if we'll be continuing this example live, or, like, I'll probably try to work it, and then next time that we come back to this, I might just present the progress that I've made, I guess. Anyways, this was fun, y'all. I had fun. Thank you for watching. You have the shape of what you need written up. Some touch-ups to correct mistakes are needed. Okay. Yeah, I think we want something along these lines, and there might be mistakes. Like, there's probably mistakes in here. But V and W are not isomorphic. But we want some property such that U and V cross W, I think, are isomorphic. So I mean, here, this looks, I would write pi W and pi V. This is uniquely determined on those arrows. Then U, like, I feel like these should actually be more like arrows in the other direction. Or am I going back to this idea of, like, the coproduct or something? Can I say that? I mean, yeah, pi V and pi W projecting from V cross W to V and W, those are defined clearly. And then from W into something, some other product space, which is has to be a vector space. if I call that function f and this function g, we gotta move on. Nope, the arrows from you are still projections. It's a bit of an annoying coincidence that the vector space direct product is both a categorical product and coproduct, so it can really confuse you. But I don't know what a categorical product and a coproduct are. Okay, yeah, so you're talking about, I see. So which direction should I be thinking of? Because you said that one direction is leading me to the categorical coproduct, and the other one is leading me to the categorical product. I think I see what you're saying now. So which direction should I be thinking of my arrows? One direction is giving me the coproduct, one of them is giving me the product, right? Or is that not even the right way of thinking of that question? Projections give you product. Projections from some arbitrary third, from some arbitrary U, projecting from U to V and W, that so I do want how I wrote it earlier, a projection. Like I was closer this way, right? And then this will like I think that the game right now is for me to define these two F and G, but this would be defined as, like, from U, I want that cross diagonal arrow, right? Pi V and pi W. So then I think it's like W maps to W cross function space. Well, like I don't know if I'm following your train of thought on, like, but this is something that I'm projections from the candidate direct product, right? From, okay, help to write out what this map pi v pi w is on elements, since you know the elements of VW. Also, what happened to not going above 3 hours? I know I keep saying that and then like wanting to like go a little more. I just want to make sure that this is a correct square and not start like this right now is the correct direction. It's the correct direction of the arrows. Again, don't try to think about maps V to V cross W. Those are embeddings, not projections. Okay. So I don't want these at all right now. That's why I feel like both of my, like this square is still wrong somehow, but I want something like this. More so. Like, don't even try to embed W into V cross W. I mean, from V cross W, I do also have these projections, which I don't even freaking know. I mean, I see these projections are clearly well defined, and those are projections as well. Is it something like that these commute, that these triangles commute? Well, you do want V cross W, just the directions of the maps need to be adjusted. Yeah, I think I just got this. Yep, commutativity is key. Yeah, so now I think that this is more in the right direction. I clearly see what these would look like. These things would just be good old simple projections. A projection to the second argument. I think that this is the better way to write it. Projection to the second coordinate, and this one is projection to the first coordinate. Right? There's better notation here. And these I want to be some other weirder projections. But this is like some other candidate product. And I don't know if that middle diagonal makes any sense anymore. Like it just doesn't make any sense anymore, but I think that there's some kind of middle diagonal between these. But pi 2 composed with f of u is equal to phi w of u. Like, I'm just trying to write commutativity right now. Like, if we first apply f and if there is a function from U to V cross W with this property, then I think that U and V cross W are isomorphic. Nice. Now unfold the left-hand side of the commutativity equation into a statement / property about vector spaces instead of just this square. What does it tell you about F on elements? Yeah, I'm not really using any properties of vector spaces other than V cross W, which is 0 V0W, and then that must map to 0W, so then therefore 0 in U maps to 0 in W, but this is anything else that we can say about vector spaces? Yeah, arbitrary elements. I mean, that's what I tried to write here about arbitrary elements. Dude, I don't mind going longer if you all don't mind going longer. I could go a little more. This is insane, dude. I can prove that I do math for fun on the internet. I mean, I feel like, you know, FU is some element of V cross W, right? Right? Well, FU needs to look like a pair. So, So, pi 2 needs to equal, like, so I see, unfold, when you said unfold this definition, on the left-hand side, I see it now, I think. Pi 2 is the projection of this, of some element like this. And I don't know what the first argument looks like. But oh wait, no, this would be pi W or phi. Oh yeah, phi W of U. Oh shit. Oh yeah. So the left, it's the same. Okay. Whoo. All right. Wait, no. This other one, I wrote pi 2 on both of these, and that's incorrect. Which one was which? Yeah, phi V U. Right here. This one should be pi 1. Right. So here's phi v of u, and the second element must be something else. But I can't say that these are equal. Is this the property that I need? That for any projection maps from like a universal product that they're equal if you use the same u for both equations. Well, fu is the same in both, right? Oh, fu is the same in both. So it's something, and then... Okay, wait, and then pi 2 of fu needs to equal wu. Like, I'm trying to avoid assuming that fu must be a pair. Well, but, no, fu must be a pair because it is in v cross w. So u maps by f to some vu and some wu, right? And then that maps to v and w by the projection maps. Like, I think that this is what we're saying, but are these... Oh, yeah. U maps to... Oh, yes. Of course. Okay. U must map to... Because I'm saying that the square commutes, then U maps to phi W, U, and phi... or phi v u and phi w u. For whatever the projection maps... I see. F would map the same u to that, which must... We have this, like, canonical... uniquely determined projection maps from v cross w to v and v cross w to u, or to w. So then any element of this alternative product space must map to these projection things. Yeah, exactly. Is this it though? Like, is this all I need? Is this the property that there's a unique F, and or like for any, or that they're all the same up to isomorphism or something, that phi W for any U, for any product space U, and a transformation map and a linear transformation in the space of LU to I feel like I'm getting closer. Well, again, you need to turn this into a statement about vector spaces in general, not just V cross W. All I need is just to rename that to some other P. Or X or something. Okay. For any two, then there is one, exactly one map from U to P. Here, this is probably best if this is like a U1 and U. Any two products of V and W okay, P is a fixed vector space which we are describing. Okay. So given what? Wait. I thought that the given fixed vector spaces are V and W. And then Are you saying for all U1 there exists a unique U2? Or a unique P? Okay, yeah. And you're saying you're using P because it's the product. And so then this looks something like this, I think. If we have a projection from, or a map from U to W, and a map from U to V, then there's a unique product or this gives rise to a unique map from U to P. The order of exists and for all should technically be swapped. Oh. Like this? It's getting kind of messy, but I think you see what I'm trying to say here. And then that unique product, I mean, like, do I draw the product somehow? Dude, I don't know. P is, yeah, there is a unique product, or there is a product such that for all... Do I say that this is a unique? No, it's like unique up to isomorphism or something, right? Or P is the direct product of V and W, and being a direct product means to satisfy that for all property. Okay. Okay, so you're saying definition of P is a product of V and W. I think this is now sounding more familiar. If P is a product of V, a direct product of V and W, if for all vector spaces coupled with a transformation from U to that vector space into V and U. Here, I really want to swap these two. Like, this is the definition of P being a product of V and W, I think. Yeah, this is kind of shorthand. I think that this is like shorthand, because it doesn't necessarily need to be pairs. You're right. So, like, such that the diagram commutes and it would formally be written out like this. So I'm going to just put this in quotation marks, but I see why you're saying that this is not formally correct. Like, what we actually want is something more like FU, yeah, the projection of FU has to equal, I'm going to now use Phi1 and Phi2 to, assuming everything is alphabetized, Phi1 and Phi2 makes sense to me. So, I mean, it's easier to just say that the diagram commutes, but I think that we're talking about... Oh, but wait, I don't even know that the projections, that these projection maps exist, because... Don't I also need... I also need some projection maps from P to V and a projection map of some kind from P to W. Because I don't have to write them as pairs, so I have to... But I do need it to act like the projections from the Cartesian product. Dude, let's just use some functional programming notation. Pi1 FU has to be the same as Phi1U, and Pi2 FU is the same as Phi2U, right? This is the universal property of product. The projections are part of the definition of P. I forgot to tell you that. Yeah, my bad. Okay. So projections are part of the definition of P. Like, we do need these Pi1 and Pi2, right? Neat. Hell yeah, dude. And now this is a universal property, I'm not actually using linearity, right? Ooh, hell yeah, dude. Hell yeah. If we can just wrap up, verify the 3 conditions. That sounds cool. Okay, so nothing is missing here, right? So P is a product of, we define the product of 2 spaces with projections if ... right? Like I should move this if outside. I mean, it's going to be hard to... Oh my goodness. You see what I mean, right? Okay, so I want to verify the 3 that is more correct in some way. Like given 2, or I could say like for all linear maps from P to V and P to W, then for all blah blah blah. But anyway, I think I see it. So now there are 3 conditions that you're saying I can check here. And what I remember was that if U1 and U2 are both satisfy that property, then U1 is isomorphic to U2. I don't know if I have it in me. I'm pretty wiped out right now. But you're saying I'm just going to leave this for myself to try to verify on my own. I want to verify this thing. I want to verify that whatever P is, it needs to be isomorphic to V. It behaves like V cross W, which I think is pretty clear. It does behave like V cross W. It satisfies, like we do have one function oh my goodness gracious. So in this square, V cross W should be replaced with P, right? In the notation that we've ultimately come up with. And now this square is completely correct. So I think. and it just more succinctly writes it. And greetings, how's it going? CD Mondays. How are you? Let me see again your three properties. A vector space with property P behaves like the Cartesian product. Okay, now this is getting confusing because P, I was referring to be the property and P being the vector space. So if P, some kind of fancy property or prop, if the property is true and the property, if the property is true for two different ones, for two different vector spaces, then they're isomorphic. Well, yeah, because then well, for all alternative products, like we can like swap U and P, right? And then that, like if there are two different candidates, U and P, then we can swap them in the corners of this diagram, and then that means that F is an isomorphism, I believe. Yeah, clash of naming. Yeah, the P being a property as well as P being the alternative product, right? But there, I feel like there's something there. Like you can swap them in the corners. I don't know if that's. I don't know, dude. P does behave like V cross W. A vector space with property P behaves like the Cartesian product V cross W. Given two vector spaces U1 and U2 both satisfying property P, U1 and U2 are the same. The Cartesian product V cross W satisfies property P. Okay, wait. So it is true that V cross W satisfies this property, and I think I see that from all the construction throughout the stream when I was using V cross W in the bottom right of this square. Like, certainly V cross W has this property. And if there are two different candidates that both map to the universal product, then they are isomorphic because you can go around the like, I wonder, like, can we do something like this? Because now this if we say that there's another this now would just be drawing both squares at the same time with the two different, with U and P both being on the top left. Like, I'm just drawing both squares at the same time, and so then we need commutativity around these as well. So then if the other square commutes, then I think that to me is showing that. How do I show? And then some sort of like F prime or a G or something. F prime, pi 2 prime, pi 1 prime. Yeah, I feel like I'm missing why that this would be an isomorphism. It's like I'm trying to show that why would this imply that it's an isomorphism, that they're isomorphic? Like, I mean, so going around the one edge, going around this direction is the same as going around this direction, right? For example, to map to W. So they have to be equal. So in like some sense, F is completely determined by phi W and phi V Oh, dude, I'm getting lost. Yeah, so the F produced from the universal property is unique. Yeah, so I was thinking, yeah, that there's only one unique Oh, dude. Having V cross W in the middle might be obfuscating things. You don't really need it. Okay, so I can do everything still with P in the bottom right as opposed to V cross W. Like back to this square. So, I mean, one thing that's confusing here is that I think that there's a mismatch of names, because here the property is defined on the product, on the potential product, right? So this should be, if the property is true for two candidate products, then they are isomorphic, right? So the fact that if the fact is true for two different products, then that map F is unique. And the fact that the map F is unique, and this property is true for all U. Since it's true for all U, then it is true for, in particular, P1 and P2. Right? So, like, we can draw this diagram with P1 in the top left and P2 in the bottom right. And we can draw the same diagram with P2 in the top left and P1 in the bottom right. Which means that we have a unique map from P1 and P2 and in both directions, and then therefore it's an isomorphism. Right? So I think that is where partly like the clash of naming, I think, may have been confusing me here. But yeah, by the uniqueness of F, right? So you get maps P1 to P2 and P2 to P1. Does that show that they must be inverses? Oh, no, right. Just because we have two maps for each other, they're not necessarily inverses, but the fact that these squares must commute and like land in V and W. I think we get it that way somehow. Let's make that more formal. Oh, geez. Swap to another color. Um, I guess I could do like P and Q or something instead of P1, P2, but whatever. So the statement says that F1, P1, and then the projection to V is the same as this other projection to V. And likewise, good Lord, I'm like losing. Okay. So I think I can like relate these. Oh, shit. Commutativity is also key. Yes, uniqueness will be applied in proving them being inverses, but it won't be applied to the maps P1. Have to go to dinner. Might be a good thing to do next stream or finish next stream. You're really close. I think I am super close. Bro, thank you so much. I appreciate it. I don't know if I missed you, but I really appreciate it. I think that we made a lot of progress here. We're still missing right now showing that any two potential products are isomorphic, but I think I just need to think about it off camera for a second. I really appreciate it, dude. Take care. I gotta go. This was a super long stream. Good Lord. Thank you for watching, everybody. Bye. Bye.